Wow, LeBron really took us into the deep blue, and now we're going to go into the skies. Our next explorer is a cosmologist who is developing incredible technology to help us see things that we can't with the naked eye. Now, National Geographic Explorers are known for seeing the world in new and exciting ways. But our next explorer has access to parts of our world that many of us don't. In fact, I was sitting at dinner with her a few days back, and she told me about how so much of her work is this process of failure and going off into the distance and looking for these incredible discoveries, but very often coming back with nothing. And then every once in a while, when they're least expecting it, they come across something that no one has ever seen before. And for that 1 second in time, our next explorer and her team are the only ones on our planet who know about it. Thankfully, they share it with the rest of us after, and they will today. But our next explorer is also really special because I think to keep at it as an astrophysicist doing such complex work without knowing whether you're going to have success or not is really hard. In the last 10 years of being a filmmaker, I've had the opportunity to meet so many amazing scientists and conservationists. And every time I come back home, I will write down in my notebook things I learned from them. When I hung out with our next explorer, Cynthia, I came back to the hotel and I wrote down, "Keep at it," because that's what I took away. So please welcome Cynthia Chang.
Thank you so much. I'm really honored to be here today. So today I'm going to tell you about how we're trying to explore the farthest reaches of our universe and to see what it looked like in its distant past. I often like to start by showing this engraving, which is appearing on the screen now. This engraving, which dates from the 1800s, and this shows an artist's impression of an explorer from that time trying to make sense of the universe that we live in. And even though there's, of course, some artistic license taken in this picture, it does actually accurately show what my team and I do for a living. We are cosmologists, and what we do is build specialized telescopes that we use basically as time machines to peer beyond the stars to try to look at the universe in its distant past. And what the artist gets correct in this picture is that what we expect to see is both unfamiliar and strange, but also really wonderful. So the question that my team and I are trying to answer is, what did the universe look like over 13 billion years ago when the first stars ignited? To put this in perspective, if you take the entire 14 billion year existence of the universe and compress it down to the lifespan of a human, the time of the first stars igniting corresponds roughly to the age of a toddler. And just like a toddler looks very different from an adult, our universe also looked very different in this early phase of its life. But if we're able to peer back and look at essentially these childhood photos of our universe, we can say something about the factors that shaped its growth and how it evolved to ultimately become the familiar place that we call home now. So the question is, how on earth are we going to do this? How are we going to get a snapshot of the universe in its past? The way we're going to do this is by building special telescopes that use antennas to measure light at radio wavelengths. So these radio waves are exactly the same ones that you're familiar with in everyday life, from radio stations and from walkie-talkies. So you can think of our telescopes as basically being very fancy FM car radios. But the difference in our case is that we're not trying to pick up signals from everyday life. We're trying to pick up signals that were broadcast during the early growth of the universe. These signals come from hydrogen, which permeates the universe as the most common element. And hydrogen has a very special property in that it naturally glows with radio light. So as the universe expands, the wavelength of this light is stretched longer and longer, and the amount of stretching depends on how far the hydrogen is from us, or equivalently, how long ago that light was emitted. So that makes hydrogen a really powerful tool for us, because in essence, if we want to study any particular slice of the universe's history, we can literally dial in by taking our radio telescopes and tuning them to the right wavelength. So that's our game plan for trying to catch a glimpse of the first stars turning on. So that all sounds well and good, but there's a catch, unfortunately. And the catch is that these radio waves from the early universe are very, very faint. And they are not the only sources of radio waves around us. So there are other sources from human-generated sources like radio towers, TV towers, and cell towers, and these sources are blindingly bright. So if we set up our radio telescopes anywhere nearby, we don't see anything from the first stars, and we are literally drowning in the noise of civilization instead. So the only way that we're able to do our science is to run away from these sources of noise as far away as we possibly can, and to go to extremely remote places. And so that's actually a lot of fun, because that means that to explore our universe, we also get to explore our planet Earth at the same time. So my team and I are very lucky to have been able to set up our radio telescopes from 2 very remote places on Earth. And since not very many people get to travel to these places, I'm going to take you on a virtual journey to both. The first site I'm going to tell you about is called Marion Island. It's a South African research base that's located about halfway between South Africa and Antarctica, about 2,000 kilometers away from anything else. So our journey to Marion Island starts in Cape Town with the SA Agulhas II icebreaker. And our journey takes us into the roaring 40s, where we sail for a few days. The conditions there are quite rough, and so the ocean swells are very large. I've been body slammed against my cabin several times, more than I can count. But after a few days, it's over, and we arrive at the island. Then we fly with a helicopter from the ship to the island, and that's when the adventure really begins. So because we want our telescopes to be as far from human-generated noise as possible, we take them several kilometers away from the main research base. So that means that our daily commute goes through several kilometers of hiking through lava rocks and mires while being constantly battered by wind and rain. I will say that this is an exceptionally nice sunny day. That's why the camera is out. You know, when there are 50-knot winds blowing, the camera stays safely tucked away in the backpack. So this is an anomaly. One of the other challenges of working on Marion is that the island is unfortunately infested with mice. It's an invasive species. And the mice like to eat everything, including our electronics, because they're drawn to the warmth. So it's been an unusual challenge in trying to figure out how to protect our instrumentation and to prevent it from becoming a mouse buffet. But despite these unusual challenges, one of the wonderful perks of working on Marion is the diversity of wildlife that we get to see. So Marion is home to countless seabirds, penguins, seals, and whales, and being able to see this stunning assortment of wildlife really is a special privilege. So the second site that I'm going to tell you about is on the opposite side of the planet, on Axel Heiberg Island in the Canadian High Arctic. So travel to the north is quite different from travel to Marion Island. And the first thing that we do is fly as far north as we possibly can with commercial aircraft. And that takes us to Resolute Bay in Nunavut. So this is where Canada operates an Arctic logistics hub that's run by the Polar Continental Shelf Program. And we spend a few days in Resolute Bay preparing our cargo for onward transport to the field. And then we take one of these planes. This is a Twin Otter, and that's our ride to our field site, which is the McGill Arctic Research Station at Expedition Fjord on Axel Heiberg. So this is a view of our research station. It consists of a few small buildings and some tents that are located next to a lake that provides our fresh water and nestled at the foot of some glaciers. It really is a beautiful, stunning place to work. So we work from this Arctic site both during spring and summer, and the conditions and challenges are quite different during these 2 seasons. So during Arctic spring, it's a very chilly time, but the benefit is that the ground is blanketed in snow, and so we're able to take snowmobiles and take our telescopes out several kilometers away from the main camp, again, to get away from human-generated noise. And then during the summertime is when things thaw out, so that's when we focus on installation activities and putting things into the ground. So just like Marion, the Arctic also has its own wildlife challenges. We have some medium-sized nibblers there that like to snack on our cables. We also have some larger nibblers that have taken away chunks of our buildings before. And in our most recent season, we discovered that there was a rather feisty fox that used our instrument as its dance floor. And there was a wolf that left its nose prints on our solar panels. But despite the challenges, it's still a wonderful place to work. So now that I've taken you on a tour of where we go to set up our instruments, I'm going to show you what our telescopes actually look like. We have 2 of them, and the first one is called MIST, and it's trying to look for the signal from the first stars igniting in the universe. The second experiment is called Albatross, and it consists of multiple antennas that are sprinkled across the landscape. In this picture, you're just seeing one of them. And these antennas work together to form a single unified instrument that observes the sky and tries to take pictures of the radio sky. So now that I've shown you these pictures, I know you're probably thinking, hold on, these are not telescopes, right? The first one looked like a coffee table, and this one looks like the world's worst Christmas tree. So when I say the word telescope, you probably think of something like this instead. This is the James Webb Space Telescope. It's a grand observatory that's out in space, and it's also trying to study our early universe, although with infrared light instead of radio. So the question you may be wondering is, how can small experiments like MIST and Albatross do meaningful science when there are large grand observatories out there like this? So to answer that question, I'm going to make an analogy for you, and I'm going to show you two different views of the same painting. And we're going to start off by pretending that we're looking at it through the eyes of James Webb. So James Webb is a very powerful telescope with sharp focus and sharp vision, so it can really zoom into the details. And in this analogy, you can see the individual paint strokes that make up the painting. That gives us a huge amount of information about how the painting was created. And so I'm going to ask a question to those of you in the audience who know something about art. Do you have any guesses as to who the painter was? And you can just shout out the answer. Van Gogh, exactly, 100% correct. So from looking at this tiny sliver of the painting, you were able to correctly guess the artist, which is tremendous, right? So that's a huge win. We can't really say too much else about the image because we don't know what the contents are, but that's okay because we already learned a huge amount just by looking at this tiny piece. Okay, so now we're going to switch gears, and I'm going to show you the picture as viewed through MIST. So remember that MIST is kind of like a fancy car radio. We're listening to all stations at the same time. So that's kind of like taking all of the colors in the painting and blending them together so that we see only the average. And I heard all of you laugh, so I know you're all thinking this is a joke, right? Because we can't see anything in this picture. It's just a solid rectangle. So what on earth can we do with this? Let me ask you a different question now. What was the weather like in this painting? I heard some people said the right answer. It's a sunny day, exactly. So, and that is, again, 100% the right answer. And it's remarkable that we were able to glean that from something that seemed, kind of useless at first. And what's even more remarkable is that we were able to get that information, and we were not able to get that in the previous view from looking at just a small portion of the painting. So now I'm going to reveal the original image. It is indeed Van Gogh and a sunny day. And you can see that by comparing the two different views from James Webb and MIST, they are very different from each other, and yet both give us very different, profound information about how the painting was created and what its contents are. So that's how small-scale experiments like MIST and Albatross are able to do meaningful science that is highly complementary to what we get from these grand observatories. Another one of the really fun aspects of working on small experiments like this is that we get to do everything ourselves. We have to design and build everything from scratch. You can't just hop online and go to Amazon.com and say, hey, I would like a radio telescope, please, one that can measure the first stars. That doesn't exist. So we have to do all of the work ourselves. And when I say we, I mean the students. They're the heroes, and they're the ones who do all of this themselves. And I like to joke that this work is really good for people with short attention spans because every day is a little bit different. So some days involve mechanical work and assembly, so really getting our hands dirty and constructing things from scratch. Other days involve working on electronics and testing those, writing computer programs. So there's a lot of variety in our day-to-day life. And the skills that the students pick up in doing this work are useful not only for radio astronomy and for building cutting-edge telescopes, but they can take these skills to basically any career that they can dream of in life, which is really wonderful to see. So I'm going to summarize by saying that our attempts to understand the early universe with radio observations have taken me and my team on some pretty wild adventures. And despite the unusual challenges and the grueling conditions and the occasional encounters with wildlife, I'm really happy to share that it's absolutely been worth it because we have found that the high Arctic and Marion Island are some of the most beautifully radio quiet places on Earth. So where we're at right now is that we have installed some of our instruments, and we are just starting to tune into the radio sky in the hopes that we'll hear the faint hum from the first stars igniting in the universe. And over the next few years, we're going to continue to install our instruments. We'll continue to observe and analyze the data in the hopes that we can fully open our universe's childhood photo album. Along the way, we made some new friends as well. And so this is another really wonderful aspect of our explorations, is that we have started exploring new research areas that lie at the intersections of our different fields. So as just one example, we have glaciologist friends who work alongside with us in the high Arctic. And we've started teaming up with them to build new instrumentation, like drones and radars, that are simultaneously useful for both cosmology and glaciology, as improbable as that combination may sound at first. So I'm going to conclude by saying that really the best aspect of our work is being able to simultaneously explore our universe and the silent corners of our Earth at the same time. We're really lucky that we're able to build these new precision radio telescopes, to operate them from remote locations, and to share our stories with you, of course. So with these new tools in hand and a clear view of the radio sky, I'll end by quoting Freeman Dyson, and I'll say that what we're really hoping for is new and unexpected discoveries because nature's imagination is richer than ours. Thank you very much.